a large structure that is directly in between the two of them. And the question is, how fast does the projectile need to be thrown so that it just clears the top of the structure? So I'm going to call the height of this structure h. I'll call the distance between the two people d, and I'll call the initial height above the ground from which the projectile leaves their hands y sub 0. Okay, so we want to know the minimum speed at which this projectile has to be thrown so that it just clears the structure here. And that means that when the object is here, it's going to be right at the peak of its trajectory, just due to the symmetry of the problem. So I'm going to make use of the fact that I know the velocity in the vertical direction at this point is 0 to do some calculations. So I'm going to set the origin for my coordinate system to be right at the spot on the ground directly below where the ball is thrown on the left side of the diagram. So I can write an equation for the vertical motion of the object between the point where it is thrown and the point where it reaches the maximum height here. Between those 2 points, I guess I'll call these point 1 and 2, I know that the displacement in the y direction is going to be h minus y sub 0. I know that the acceleration in the y direction will be negative g, and I know that the velocity in the y direction at point 2 is going to be 0. So I can use this to figure out what the velocity in the y direction must be at point 1. The equation there would be the velocity of y at point 2 squared is equal to the square of the y velocity at point 1 plus 2 times the acceleration in the y direction multiplied by the displacement in the y direction. So when I plug in everything that is known, that becomes 0 is equal to vy1 squared minus 2 times g times the quantity h minus y sub 0. So that means the y velocity must be the square root of 2 times g times h minus y sub 0. Okay, so I know what the initial y velocity of the object must be. Now, if I can find the x component of the velocity, then I can combine those and find the magnitude of the overall velocity. All right, so in the x direction, I know that the object has to travel half the distance between the two people during the time that it takes to travel from point 1 to point 2. All right, so what is that time, first of all? Well, if I know the initial y velocity now, I know the y velocity at points 1 and point 2, I know the acceleration in the y direction is negative g, so I can find the time by using the equation vy2 is equal to vy1 plus the acceleration in the y direction times delta t, or in other words, 0 is equal to vy1 minus g times delta t, or delta t is equal to vy1 divided by g. Okay, so I have an expression for the y velocity at point 1. I can calculate that and then plug that into this equation and find out how much time the projectile has to make it from the point of being thrown to the point at which it is right at the top of the obstacle. Once I know that, I can turn to an equation for the horizontal motion. I know the displacement in the x direction is just going to be the x velocity at point 1 multiplied by the change in time between points 1 and 2. I guess I could write this a little bit more explicitly as, t2 minus t1 if you prefer. All right, so what is the displacement in the x direction? By the time it reaches the peak of its trajectory, it's traveled half the distance between the two people. So I'll have 1/2 d is equal to vx1 multiplied by delta t, or vx1 is equal to d divided by 2 times delta t. Again, I have a way to calculate delta t from before, so I can do that and then plug that into this expression and have my horizontal velocity. So now I know what the horizontal and vertical components of the velocity must be at launch. So I can find out the overall velocity using this relation here. All right, so once I have my horizontal and vertical components, I can find the overall launch velocity simply by plugging those into this Pythagorean relationship. All right, so that should just about do it. Thank you all for watching.